My name is Robert Breeden. I'm also an applications consultant. I've been with the FG Wilsons for, it's the 30th year this year, so I have some experience of generators, and I've worked in design, test, and I've been on applications for probably the last 5 to 10 years. So this afternoon, I think lunch is going to be about 1 o'clock, so you've got about an hour to listen to me at this stage. So I'm going to, first of all, talk about generator selection. So the selection of a genset, actually the application of the genset to the application is very critical. And there's some key elements that we need to really consider when we're matching the genset to the application. So some of these are quite obvious. So obviously the kVA, kilowatt requirements. What types of loads are we actually having to supply? The transient response that's required. So if the machine has to pick up a very large load, how does the machine react to that? So we have to deal with the transient elements. And then probably more importantly is the nonlinear load. So if you have a lot of power electronic load, UPSs, linear speed drives, we have to consider that and the effect that may have on the genset. And of course, applications change season or actual in production, so we need to think about the application as in the round and what happens during different seasons or different times of the production. So, and that's just a quick summary of the key elements of gen selection. So probably the majority of loads that a genset has to supply is a motor load, and in very basic terms, the motor, when you apply a motor to a genset, it initially on starting will see 68 times starting current. So that creates quite a high impact requirement on the kVA and the kilowatts of the genset. So we have to be able to deal with that, and the easiest way to do that is to employ a starting method like some form of voltage reduction, reduced voltage starting. Probably the most common type is the star delta method, but there's various types, and we, as Johnny says, we get involved in quite a lot of projects, maybe some high voltage projects where you'll have very specialized starters, and we need to look at them in more detail. But the key thing we're trying to do here is reduce the impact of the starting kVA and kilowatts to the genset so that we don't have to oversize the genset and provide a very big genset for starting and it's vastly oversized for its normal running requirements. So as you can see here, in a situation where you have a star delta, you start in star, and that will reduce the voltage to the genset or to the motor. The motor obviously then will provide the genset will see a less kVA demand, but this is something that always has to be considered. When you're transferring between star and delta, there is always going to be a peak, and our genset, when you're selecting it, has to be able to overcome that. So in a one-off situation, that is fine, but if you have lots and lots of motors and this is happening, it has to be considered. And as Johnny was saying at the very start, we have a lot of tools to provide this selection. One of the tools is GenSelect, and we have the ability to model different starting methods like star delta in that software tool. Variable speed drives, the ideal situation with variable speed drives, they limit this starting current to about 150% of full load current. That means there's less of an impact on the genset for starting, but the most important element of that is the harmonic distortion that may deliver, the nonlinear load that the genset will experience. And depending on the quality of the variable speed drive, that can also have a major impact. So we need to consider that very carefully, especially when you get lots of these. We have had an application in London for a very famous media company, and they have hundreds of speed drives and they have lots and lots of LED lighting, and it has caused considerable problems because the machine was undersized. We had no we did not get involved in the sizing at the start, and it has caused a lot of problems. So And these are modern variable speed drives. And there's a lot of LED lighting, and you just have to be careful on the non-linear element. So the other big concern when you're selecting is transient response. So when you put a large load step on a genset, it doesn't have an infinite capability. It will slow up, the frequency will slow up, and the voltage will drop. So to be able to overcome that, we have to be able to provide a good response from the governor, and we also have to have a very good response from the AVR. So the AVR plays quite a key role in the response in transients. So a typical AVR function is obviously to regulate the voltage output as the load changes. So typically our AVRs will provide plus or minus 0.25% regulation at steady state. But they also are very important when you're actually taking a load step on. And the ability to actually respond to the load and actually provide relief on the engine is quite critical. And if we look at our excitation methods, so there's three sort of different excitation methods that we use. The simple one, the standard one, is self-excited. So the power for the excitation is taken off the terminals, same as the monitoring or reference voltage. So that's 90% of the product that we supply would have this type of excitation, and it's also known as shunt excitation. The other method that we use is ARP, which means that the power for the excitation is taken from an auxiliary winding within the alternator. And that means that any outside influence or issues that are going on in the outside world, like large drops in voltage, are not experienced by the power circuit of the AVR. So it allows us to continue to force fault current and also to be more stable when we're starting large motors. And that's just a cutaway of the winding embedded within the stock. So this alternator is bought and manufactured with an RF winding already installed. The other method you may be familiar with is a PMG. So that's like a separate genset or alternator that's mounted on the end of the genset, and that provides again the excitation. If I'm going to consider, so we get a lot of questions, which method is better, PMG or ARP? Well, you can see that they both have the same key advantages. Been able to start large motors, high starting capability. They also can force fault current, so your protection will operate properly. This adds no extra length, so there's probably a slight advantage in this, and there's an intrinsic build-up, so that's quite important. The shunt method, as you can see, self-protected, so there's no short circuit capability and there's no extra length. So the key things, the difference between these two from a disadvantage, it is a specific winding, so you have to purchase it with your machine. Whereas on the PMG, you can add this usually as an extra if you need to. So that's just the two key advantages. The shunt machine is very poor at dealing with short circuit capability, low starting capacity, and if you have a lot of distortion on your load, it may also affect your voltage output. So that's a quick summary of the excitation systems. So Johnny sort of referred to all the different types of testing that we do, and he went through that in quite a lot of detail of the overview and the amount of investment that we've made. So when we're providing test data for systems, we test everything to ISO 8528. That's the standard, the generator standard that is used for vibration, for load acceptance, for ratings, and it's got about 10 or 11 different clauses. So we will test our machine to ISO 8528. We also will look at a cold load acceptance, which is slightly different to what is outlined in the ISO standard. And the NFPA is something that we can test to, and we do test from a solutions and a project environment. So I'm assuming everybody in here has maybe heard of class G2 and class G3. And this is really the performance of the machine when load is placed on the genset or rejected. And typically, the majority of applications will be based around G2. Of course, all the gensets will meet all these classifications as a load acceptance, on a load acceptance perspective. But the tighter the frequency requirements, so if you put a load on the machine and you're only allowed the frequency to drop by 7%, that is a much tighter requirement than G2, which allows you to go to 10%. So unless your load really requires a very tight regulation, G2 is more than acceptable for the majority of applications. So in an ISO test, effectively what we're doing is putting load on the machine and checking that it will do a load step sequence and reject 100% of its load and stay within the regulations that we stated. So on full rejection, the machine must stay within, if it's a 55 hertz, it cannot go above 55 when 100% load is taken off the machine. Now, there's a lot of queries about how does an ISO standard actually defines how you actually, or how much load is put on at the first stage, and it bases on the BMEP of the engine. That's the brake mean effective pressure, and that again is in the standard. So when we're testing an engine and providing a G2 performance, from an ISO perspective, this is the BMEP. So each engine will have different brake mean effective pressures, and this is the. So if for example you had 2,000 kPa of a BMEP, the first load step that the ISO standard would require is 40%, and that is defined in the standard. Now, of course, a lot of customers will ask for 50% to ISO. That is they've defined a load step to the standard, which is sort of two different things, and we have to be very careful how we address that. We have selection for G2. We know exactly how each of our machines perform, and we can give you very detailed information on what the maximum load step is for the machine. And normally it is well above what is specified in the standard. But what I'm referring to here is if someone defines the requirement to be ISO 852 G2 load acceptance, and they don't put a load step requirement, this is what we would refer to, and this is what we would reference against. So what we could, sort of probably one of the most important sort of tests that we do is cold load acceptance. So a cold load acceptance is really a real world incident for a standby machine. So if a machine's sort of working, sitting in a critical environment, and it has to start and provide the load, we want to make sure that we know how much load that machine can accept in its first load step. So in this particular case, you're allowed jacket water heaters to be on overnight for this test. The other test, the engine was run up and on full load, and then and taken up to working temperature before any of that testing was carried out. So this is a much more stringent and a real world application method. And this is just a couple of charts showing a performance on a P2000-1. So in this case, this roll-off thing we talked about the AVR earlier. The AVR is actually reducing its voltage as the frequency drops off during the load step. So what that does, it actually means that there's less, the engine or the alternator is seeing less electrical kilowatts, and it allows it to recover. So if there was no voltage slope or no relief in this engine, we wouldn't be able to provide as high a load step. And that is how all the manufacturers, all our competition use the same method when they're quoting load step performance. They're not just basing it on the engine, they're basing it on the genset and the alternator performance. And this roll-off function is very critical to allow them to achieve the step loads that they publish, and that's how we operate as well. So it is we just have to we try to obviously optimize the ramp rates, etc., to make it as good as possible. Again, this is for normally this test, and I don't know if you've ever been at witness tests. The only time the genset in many instances will see this type of operation and type of testing is at witness test. In the real world, it never probably is required to accept anything like this type of load. And if you were designing a building or an application, it would be very poor design profile to actually try to impact the machine with a very large load, which could cause problems for your tolerances, your voltage systems. If you can manage the load, it's a much better method of attack, a much better way of putting your system design together. NFPA, Johnny referred to it earlier, and that is a standard that has been in the industry for gensets for a long time, especially the NFPA 110. And the way that they used to look at this was the machine had to accept 100% load and not fall over. So instead, there was no voltage or frequency classification. 100% of the rated genset load was put on the machine, and the key thing was the genset had to continue to operate, so the frequency and voltage would eventually return. So NFPA sort of, and with the lobbying of all the engine manufacturers, they removed the requirement for this 100% load step requirement back in 10 years ago. They seen it as, well, it's not a good thing to do to your engine. A brand new engine, and all of a sudden you're hitting, especially the large 16 set large engines over any turbocharged engines, and they basically were lobbied by all the engine manufacturers to take this out, because initially this was designed for a dedicated genset against a dedicated pump for a life safety environment. So it was probably a 50 kilowatt or 100 kilowatt motor, and it was probably a 400 or 500 kVA genset. But this crept into machines that were 3 MVA, 2.5 MVA, and it was not really, not really sensible. Now, again, we live in the real world, and we know that we can achieve this, and we still get requirements for it. Slowly but surely, it is falling away from requirements, but from specifications. But unfortunately, they're still in, and it takes a long time when specifications are written, copy and paste. Consultants will use the same specification over and over in many cases, and eventually they will remove it. But we, of course, can do 100% load step. So in this particular instance, this is a 2.5 MVA machine, and we're placing 2 megawatts of load in one step. Now that is quite amazing, because this engine is typically around 55 to 60% within G2. When you place that amount of load on at one go, it's just amazing how it can actually respond. So again, what we're doing here is removing with the voltage slope, we're taking voltage off with the frequency fall off, and the engine actually eventually will stabilize and return. I think still it's a very hard thing to do on your brand new engine, but some customers insist on it. So just a quick summary on load acceptance. Voltage regulator plays a very important role. I said G2 is acceptable for most applications, but of course we can provide machines that are G3 or even G4. So you may, I sort of skipped that bit, but G4 is an instance where you have a very dedicated requirement for your load. We had an application with a liquid gas pumping station a few years ago, and the electric pumps in the gas had to start within 5 seconds or 6 seconds. It was a very quick start, and they had very tight criteria on the voltage dip and the response. And when we selected that machine, it was selected against that particular. It wasn't a G2, it wasn't a G3, it was a G4. Because if we didn't start the motors and we allowed voltage to stay on, the motors would just have burnt out. So in some cases, you have to be very careful with your selection for specific projects. As I say, the majority of applications in the world, G2 is more than acceptable for them. Cold test is basically simulating a real world situation, and as again, we don't like doing it, but we can provide 100% block load capability if requested. So we were talked earlier about different applications. The non-linear load is quite an important load to consider when you're selecting the genset, and it can cause lots of problems if it's not done properly. It will eventually probably destroy other equipment that the generator is connected to, because the voltage waveform will become so poor that it can cause the distortion levels will be so high that there will be heat buildup maybe in some of your more sensitive connected load. And of course, it will probably damage or burn out or overheat the alternator. So we need to be careful in the selection. And again, our selection software provides that capability and will select the right alternator for the application. And what we're really doing is, in simple terms, we're putting a larger alternator. There's more copper in there, and it's able to provide a better, basically synchronous alternators are like a filter, and so they will try to filter out harmonics. But there gets to a stage where there's not enough capability. So when you oversize, you actually they do smooth out the waveform to some degree. But if you don't have enough copper in there, and I'm talking very simply, it's a lot more complex than this, they will overheat. All the levels of harmonics will eventually cause an overheating situation to occur. So just some examples. So medical imaging equipment, battery chargers, computer power supplies. I don't think the computer power supply that for your laptop is probably one of the most non-linear and because they're very cheap. So the quality of the power electronics in there is fairly low level. So they're not what I'd term a very clean or they're highly non-linear. So it's okay for one or two, but if you have a large office with lots of these, again, that can affect your non-linear and your harmonics in your building. And one of the things that's not up there is LED lighting. So LED lighting, the drivers for the LED can cause a lot of problems with distortion, especially, again, back to that building we're talking in London where there's hundreds of thousands, maybe millions of LEDs, and they have caused problems. They weren't considered in the initial design brief, and we've actually had to supply another genset, much oversized, and in fact, one of the gensets has been taken off, and we're putting a larger alternator on. We're putting a larger alternator on the machines, a high voltage machine. So that's the sort of impact this can have if it's not considered, and that's why in complex applications, the applications team in Larne, we like to consider them because you can end up in a very difficult situation that you have enough kilowatts to drive your load, but your alternator's burning out or you're damaging other equipment. So we can help with that We have a team that can help with that selection if you have more complicated projects. I'm not going to spend having much time. So UPSs are really, you've got an AC, DC rectification. The older equipment was a bit more, wasn't just as sophisticated and was highly nonlinear. The more modern UPS is a bit better, and it's got active filters. It's got a lot more technology to lower the distortion. And this wasn't driven by the generator industry. You had power utilities. The amount of equipment that was going on to the power utilities and affecting their networks, it became absolutely imperative that they done something. So they set very tight guidelines. And I know of applications and probably in industrial areas where there's been so many buildings put in, and the customer at one stage has to, this is for a utility connection, and they had to either put active filtering in or do some means of determining to limit the non-linear load, because they wouldn't be allowed to connect, especially in a lot of process or maybe where there's a lot of drives or non-linear load. So that is a very real situation that happened in UK. So that's where a lot of the active filtering technology came out. So people were putting active filters at the front end of your connection beside the input side of the mains. So UPS normally ramping. So we talked about impact loads. UPSs do not normally present an impact load. The only time that may be a problem is if the UPS goes into bypass. So all the load that's connected to the UPS, the genset will see. So that's probably something that needs to be considered if it's a lot of your load your sizing is based on the UPS. You may need to take some review of that. But normally in normal applications, UPSs walk in. So from a sizing perspective, we need to always sort of provide a genset that covers the running load. That's quite a straightforward statement. We need to be able to ensure that the genset will provide the power in a sensible way and keep your voltage and frequency within nice tight tolerances, so that the quality, so you're not seeing lights dipping or as the load goes on, or you're causing other issues with other parts of your equipment dropping out. So that's very important. So the quality of the output and how the building works, the selection of the machine and how you size it is critical to that. And if you've got a lot of non-linear load, that the load is the genset or the alternator is selected to deal with that. Possibly in that last point, as I say, a lot of more modern non-linear equipment, power electronics, UPSs, variable speed drives, they have become a lot better and a lot cleaner loads. But if you're selecting a genset where you have a mix of load, or maybe you're selecting a genset with a lot of older UPSs, you need to be very careful that you select the right combination of machine. And again, we can support you in that. So that was genset selection. I'm going to talk through ratings. So this, and I know Jonathan and myself do get a lot of these questions, why can I not get 2,500 kilowatts out of my 2.5 MVA alternator? I can get it out of my 2.5 MVA transformer. And the reason is, obviously, we have a limited power source. We have a prime mover that has a certain capability. But you would not believe the amount of times I get asked this question, and people actually saying that we're not providing the right product, or you're underselling me something. I've been in that situation on a number of occasions. So the key thing is the power of the machine is limited by the engine power. So in the generator 50 hertz world, we rate everything as a kVA based at 0.8 power factor. So in this case, the 2250 kVA machine will provide 1,800 kilowatts. So the 0.8 power factor is just a standard that's used. The machine obviously can work up to unity, maybe slightly into leading, and less than 0.8. But it's just a reference point that we use for rating the machine. 60 hertz, of course, the basis of it's based on the kilowatt. output. That's how it's normally referenced in the 60 US world. So ISO standard defines different types of applications. So the same genset can be selected for different roles and different types of modes of operation. So prime power is where you have, it's the sole source of power, and there is no other backup. Standby power is where you're standby usually to the mains. Continuous is where you're operating continuously at a set base load, probably in connection with in parallel with the local utility, or it could be an application that is just, when you turn the genset on, that is the load that the machine sees for its entirety of its operation. And finally, which is a rating that has probably come in the last 5 years, 10 years, is data center continuous for data center applications. So I'm going to sort of quickly work through. So prime is unlimited hours per year. The standard defines the application as a variable load at 70%. FG Wilson's machines are rated at 80%, so we're about 10% higher on an overall average. You're expected to be able to provide 10% overload, and it's usually sort of rental type, industrial pumping. There is instances, of course, where customers will ask for prime power, but they're really looking at for a standby application, and we do get a lot of that instance. And I know that sometimes you're looking at the rating. Really, from a perspective of that, the machine is this. So if we have a 2500 or P2500-1, that machine would provide 2500 kVA standby. It also will provide 2250 prime, and with 10% overload, 2500 kVA. So we're really looking at the end of the day, this is a risk management, a warranty management system. So in a situation where we provide the same machine for standby applications, it's at 2500 kVA. Again, it's variable load around that rating, up to 500 hours per year, and there's no overload permitted. Again, we define and we look at applications very particularly, and in some cases you may have a standby application that's going to be running a lot more than just over 500 hours. That's tending into prime territory. So again, we look at these on a case-by-case basis. Continuous power is probably the most difficult and hardest application for a genset. So if you think a genset starts, it runs to its power and it stays there for how long it runs. So in continuous applications, if you were to take a prime machine and run it at continuous rating, you're just going to shorten its life. It's not designed to do that. So we would typically look at a prime rated machine. You would run it at 70 to 80% of its output as its maximum point. Again, base load of utility, applications where you're paralleling, supporting the grid, that type of situation. Data centers, and I came up with this. I was sort of doing some research, and I seen this word zettabytes, and it seemed a bit strange. And today, if you think of zettabytes, 1 trillion gigabytes, and it's hard to get your head around that number. So today, we're using about, in 2018, we were using 33. By 2025, that will have, 6 times, it'll be 175 zettabytes. So to back and support that, there's a lot of data centers going to be required. And even, if you think of the amount of streaming that we do, so they're saying by 2021, 67% of internet traffic will be content streaming. Obviously, 5G systems are coming on board, connected systems, your Internet of Things. everything that we do today requires data in some form. So there has been a continual growth of data centers, and this sort of is some reference from IDC and from, I think, IDC. And they're looking at data center growth from 2017 to 2025. Basically, the traditional data center is going to double in requirements per year. Now, probably something that this edge data center, and we're probably going off a wee bit here, but the edge data center is going to be closer to things like autonomous driving cars or your Internet of Things or even your streaming. So for real-time streaming in your phone. Because the problem with the larger data center, it takes longer for the information to get. Now we're talking milliseconds here, but the larger data center requires probably 70 to 80 milliseconds, where they want this to be down to 5 to 6 for real-time management. So there's going to be a lot more smaller decentralized data centers closer to connected devices to cut down that latency. And there's going to be quite a growth in that in the next 5 to 6 years. And it's all driven really by our requirement to have real-time control. A lot of the control will be and processing and processing systems will be done at these edge centers, whereas the centralized data centers will still hold the core of all the data because you don't need all your data at once. So these things will work in conjunction. And I know there's probably a data center guy here who will probably be giving a lot more information later on in this, but I see this as, in summary, the requirement for gensets to back up data centers is not going to go away in the short term. And you know, looking at it from a selection perspective and going on from how we look at it from a genset, the data center is two critical loads that needs to be considered. The UPS, which is backing the critical servers or computers, and then the cooling load. So computers generate a lot of heat. When you put a lot of racks of computers together, they generate a tremendous amount of heat, and that needs to be managed by chillers and air handling. So that is normally when we're supplying a genset into a critical data center, that's the loads that they're going to experience. So looking at it from a UPS perspective, again, UPS is, if you're selecting a genset just to, to back up a particular size of UPS, you have to consider not only the rating of the UPS, but when you're supplying the load, you want to also recharge the batteries. So that forms an important element in your selection. And if we're looking at our selection software, we can actually either have a certain level of recharge or no recharge, because some customers go, it's a standby environment, your genset's going to be on for half an hour, we'll go back to mains, and the mains will recharge the batteries. And customers do look at it from that perspective. As we said earlier, the modern UPS probably doesn't just present as much a problem as the non-linear load. But what we do see in specifications and requirement is if a UPS for some reason trips out, falls over, the critical load is still there, and the genset will still have to provide power to that critical load. And because of the power supplies, etc., that are in these servers, almost certainly they will present a leading power factor to the genset. Now, gensets, this is what they call a capability curve. So this is where the genset likes to operate. So this is lagging from unity power factor to 0.8. So as you can see, that's quite an easy area for it to operate. It can operate at leading power factor to some degree, but again, we need to select the machine very carefully, especially if we know there's going to be a possibility of a lot of bypassed server load could be placed on this genset, because if we get into this red area, we can have all sorts of problems voltage instability. So again, selecting the machine in environments where you may go into bypass. Now, the good thing is normally you have a lot of inductive load with the chillers, etc. So they usually counterbalance, but it really depends on your selection or your application and the balance of the load and how much UPS could potentially go into bypass and how the UPSs are arranged. So again, that's something that, I have seen in a lot of cases where the consultants have asked for, can the machines operate at, say, 0.95 leading, because that's what they're considering the bypass situation to be. Normally UPSs, when you're connected to UPS, you'll not go. You'll set about unity power factor, the most efficient level. So Uptime Institute, basically recognized as a major certifying body within for world data centers. Not everybody uses them. Some of the big guys, players will have their own strict methods of certifying and are big enough to not really worry their name carries them forward for their reputation. But this is really a risk thing. So if you're going to use a data center to spec up your critical data, you want to make sure that it's not going to fall over, that it's going to be available to ensure, because when it falls over, it'll cost you money and reputation, etc., etc. So we sort of work with Uptime guys to be certified to deliver, be able to deliver Tier 4, Tier 3 certification approved models, what we call our DCC ratings. So we are authorized to sign letters for applications. So when we're signing that letter, we're looking at the ambient. Johnny referred to it earlier, the ambient, the altitude, the actual room location, how it actually operates, so that when we're saying the machine will deliver the particular rating at a reference point, and they use usually an international reference, the company called, or international body called ASHRAE, they will use reference data so that you must make sure that your machine can deliver the ratings in that sort of application. So Uptime have sort of defined that the machine is able to run unlimited hours at end demand. So that means that if they say your machine is a 2000 kVA, it must be able to run at 2000 kVA and have no variation, basically at 100% load factor. And they don't require an overload, but in lots of cases we do deliver that as part of our standard rating. It's just something that we're able to offer. Just a quick summary of, this is just some of the models that we were able to provide, right through from 250 to 2 megawatts. This just doesn't happen by accident. We just didn't create these ratings. We worked, as Johnny was referring to, the development work we do with Perkins. We worked in conjunction with Perkins. We looked at how these machines will operate under these conditions, and we've done a lot of work. So Perkins backed us up and supported us on how we deliver these ratings. So if, for example, your customer says, well, have you any support from your engine, from the prime mover? We have letters to support that. We have a lot of technical data that will support that. So FG Wilson just hasn't done this on its own bat and decided this machine can provide this. It's been a fair bit of work between ourselves and Perkins. Basically, the other thing that's probably come in the latest ISO standard has got a rating called DCP, Data Center Power. It's consistent with that. I actually look at that, if you've looked at that definition, and it's a very open, it's not a very stringent definition. I would say that our definition and what we're offering here is a lot more stringent. But you will see probably, and we do see some reference to that, but we are totally consistent with that. And with our product for DCC, we can go up to 2 megawatts as our highest rating. So more application sort of work, and probably Johnny's Johnny done a lot of work on this site. I think he lived on this site for a while. He got frostbite, I think, on one stage at this site. Did you, Johnny? Very cold. So this is a site just south of London. There's 90 MVA of 11 kV generators. One of the critical requirements, again back to planning and environmental requirements, was the noise level. So there's a lot of probably residential homes not far from this site, so they had to meet a very strict noise. So 60 dB at 1 with, these were what we termed twin packs. So we had two 1500 kilowatt machines connected together. And they went into groups of about 20 normally, and they synchronized it together. But as you can see, there was quite a lot of, the installation is roof-mounted radiators, so we couldn't bring the air through the container. It's just too noisy. We had to take the cooling remote from the engine so these are quite quiet operating remote rads. So that's just an example of a data center that we've done. I've another one that I just want to take through. This is a video of one of our important one of our dealers in Norway. Sorry, the sound doesn't seem to be. So I'll talk over it here. So this is a co-location data center that
the infrastructure for our customers.
Okay.
That business is currently growing really fast. The delivery from Coromatic is a part of our critical infrastructure, supplying power to our customers. We have customers within several segments, within a bank and finance, the health sector, the cloud sector. The solutions they are running in our data center is at a level that it can never fail. And that is why we have to secure our power delivery with a backup generators. It's a critical part in our delivery, and it helps us to achieve the SLA we have to our customers, and until now deliver 100% uptime on both our facilities since the start. The strength of having Coromatic as a partner is a lot. It's their ability to understand our needs as a customer. It's the ability to put that into a design based upon those quite let's say rigid requirements we have. It is their ability to be able to deliver the solution as requested, doing a handover, doing the testing, and as well follow up the equipment during the lifetime with maintenance and what order needed to have a solution that is running every time we need it.
So that's one of our dealers in Norway. And if you replaced, so what they provide and bring to that particular customer is the exact same thing that FK Elektra can do for you. Do it better, I would say. So the key thing is that we have the ability to deliver data center rated gensets that will deliver your power, your uptime power continually for your applications, and that's just an example.